Well, first today's talk is going to be Isacco Nonino from the University of Glasgow, and he's visiting. He's an IMSA visitor officially, and he'll be visiting for basically 2 months now, 2 months from last week. And before we get on to this talk, I just make introductions here. We've got Nikolai Savelyev, Christopher Scaduto, and Sinem Unaran. At some point, I expect Fabiola Maharaj Gutierrez to come in. She got another IMSA visitor who got here on Tuesday. And Nonino is I guess a grad student of Andy Wand and Aquana.
Yeah,
both of them. Yeah. So I forget the title of your talk, but he's going to tell us about contact structures on hyperbolic surgeries, genus 1 fiber knots and lens spaces, or something like that.
Yeah, it's a long title, but it's
all right.
Welcome everybody, and thanks for the chance to give this talk. So I would like to let's say introduce my work I've been doing recently, and this is kind of a classification result for tight contact structures on hyperbolic tree manifolds, which are notoriously interesting since they are not well understood in general. And these manifolds come from rational Dehn surgery on genus 1 fiber knots in lens spaces. And here on the whiteboard, I wrote a statement of a theorem, which I will try to prove during, I think, 2 talks, if that's all right. In this first talk, I will do, let's say, the first portion of the proof, and maybe in the next talk, I will do the second one. It's a natural splitting, and you will understand why. So the theorem states the following. I take M, P, and K, which are positive integers, satisfying these 3 conditions. So R is greater or equal than 5, P is 5, P is greater or equal than 2, and K is greater or equal than 2 as well. I call L M K P plus 1 over P, which is just the 3 manifold which I obtained via this rational surgery, Dehn surgery with this coefficient. On the genus 1 fiber knot K2, which I drew here with a mixed link diagram inside the lens space LM1. Then this manifold admits exactly, 3p plus 1 if k is equal to 2, or 4p if k is greater than 2, tight contact structures up to isotope. So for today, I would like to focus on the first part of the proof of this theorem, which relies on finding a lower bound for these tight contact structures. Namely, I want to focus on the, let's say, this portion. So I want to construct, let's say, 3p plus 1 if k is equal to 2 and 4p tight contact structures, and I want to be able to distinguish between them up to contact isotopy. On the next section of the talk, I would say, so maybe in the following talk, I will discuss the second portion of the proof, which is finding an upper bound, so determine how many possibly tight and possibly non-isotopic tight contact structures this object can have, and show that this upper bound and lower bound actually match, so we get an exact number of tight contact structures.
So this picture is the surgery.
Yeah.
The team center is K1?
Yeah, it is. Yeah, sorry. I write really small. I should write bigger. Yeah, this is K1. This is K2.
Oh, there you go.
Yeah, okay.
And K2 plus 1 over P is the surgery rate.
Yeah, of this one.
On K2.
So,
With respect to S3 frame.
yeah, this is in.
The K2 is no homologous.
Yeah.
So. And the complement table.
Also, I would like to give a premise today. For the purpose of this talk, I will just explain the k equal to 2k's. I mean, the k greater than 2k's is basically the same. It's just a, let's say, more general computation, and I don't want to bore you with all the calculations, but I think it's easy to understand when you see that with k equal to 2, and it generalizes pretty easily into the greater numbers. So we will actually work under this assumption. So as I said, I would like to construct 3p plus 1, in this case, tight contact structures, and distinguish between them up to contact isotope. So we start with this surgery description, which I will redraw here. And so now I am, and this is 2p plus 1. So first of all, one thing to notice is that I have to do this. This is actually equivalent to just whited ink. This is actually the same surgery, and we will use this fact. So keep this in mind. And so first of all, what we do here is perform a right-handed rose and twist on the unknown portion, and we finally obtain this picture, which is the one we will be working with. And here. So now the surgery coefficient here changes to this guy here. And this is 2p plus 1 over p. Notice now that this is just this guy here is just right. Okay, so this is my working picture for the surgery diagram for this manifold here, and I will first need the following simple lemma, which is, I would say, just a number theory thing. So let m greater or equal than 2, then the continued fraction expansion of m is given by, sorry, not of m, of minus m over m minus 1 is given by this guy here, m minus 1 times, in particular, this is just a bunch of and so on. So this is m minus 1 times. So the continuous fraction expansion, for those who don't know that, it's just how do I write this rational number in as a sequence of this form.
In particular, using the topologist's continuous fraction.
Yeah. This is like each one has to be less or equal than minus 2.
And you're also using the negatives.
Yeah, the negative ones.
And you're asking that.
Yeah.
Each coefficient is less than or equal to.
Yeah. So on. And so. So for this, my minus m over and -1, the continuous fraction expansion is just given by a sequence of -2. So what I can do here, just the usual thing, I can take sequence of blow-ups and transform this surgery description into this guy here. So the unknown portion becomes a sequence of just a chain link, a lot of them, and then I get to this portion here, and here I have my right-handed traphoid. Yes, -2, and here is 2b plus 1 over b. Okay, this is so far so good. And now I want to, yeah, yes,
Yeah, after the Rolfson twist.
yeah, after the row.
Change that component to a.
Alternative. It's not alternative.
Oh,
It's for crossings, but it's not,
Oh, it's
not,
for
not
crossings.
overnight.
I was right, I see. Yeah.
Yeah.
So fun with you. Thank you.
Yeah, okay, maybe this portion here is, yeah. So now we have to play with the contact structure. So I want to take the generalization of this surgery diagram, and I take this one here. So sorry, I have to draw up pictures. Here, like this. Now, well, this graph goes here, and this is for the unknown portion, and then you end up with the is correct. So this is the generalization of this part here.
What's going on down there?
Yeah, maybe it's
Yeah, so how's that trefoil linking the other?
yes. Wait for a little second.
Because your Legendarian has a bad crossing there.
Yeah, maybe I will like mess up pictures when I draw them. Yeah, and now you have. Yeah,
There you go.
yeah. Sorry. And as for the surgery coefficients, now I want to have the contact surgery coefficients. So I will subtract the Thurston-Banach number of these guys here from the smooth surgery coefficient. I get these guys that will have coefficient -1, and this guy here will have 2p plus 1 over p minus 1, which is p plus 1 over p. Okay, so I have my Legendarian surgery diagram, and now what I want to do is turn this into a plus or minus 1 Legendarian surgery diagram. And to do this, I will use the usual thing guidance algorithm. I mean, here there's nothing to do. It's already a -1 Legendarian surgery. I have to work with this portion here. And to do so, I will erase this portion, which is not right. To do so, I have to turn this first of all into a negative coefficient. So I take m such that the minimum m such that p plus 1 over p minus and p plus 1 is less than 0, which is just n equal to 1. And now the coefficients are is equal to p plus 1 over p minus p plus 1, which is just minus p plus 1.
So if you say again what you're doing there?
So what I want to do is now transform this portion here into a sequence of plus and minus 1 surgeries. And basically what the algorithm tells me to do is, first of all, I take the minimum n such that this fraction here is less than 0, and in this case n is just equal to 1. And then I take the corresponding value, so r is just p plus 1 over p minus p plus 1.
So you're going to take the minimum, so you're starting with p plus 1 over p.
Yeah, I take the minimum
and then you're take the minimum into that p plus 1 over p minus times the numerator.
Yeah, it's just like a changing matrix basically. And this becomes now negative, and this is my new surgery coefficient.
Becomes non-positive.
Yeah. And so what I do now is just take I do first plus 1 surgery on the original right-handed trefoil, and then I take a Lagrangian push of L of this, of let's say K2, and perform R surgery here, where R is minus p plus 1. So I do plus 1 surgery on my original trefoil, and then I take a Lagrangian push off of that, and I perform this negative surgery on that. And to turn this into a sequence of minus 1 surgeries, I just need to stabilize this guy. Stabilize L p times. Yes, and so the point here is that this. Now I want to understand how many possibly distinct tight contact structure I constructed like this. And first of all, one thing to notice is that here I'm doing positive surgery on the right-handed trefoil knot with Thurston-Banneking number equal to 1. And by result of Liskay-Matic, this preserves actually tightness. So the resulting tight contact structures the resulting contact structure of this surgery description actually tight. I mean, this one is just minus 1 surgery, so that's fine. Second of all, I want you to notice that here I'm doing stabilization, and precisely each choice of stabilization will give me possibly distinct tight contact structures, and I will show you later that this possibly distinct is actually translated to actually distinct in terms of contact isotopic. So I actually constructed here, counting the choices, different choices of stabilization, I constructed p plus 1 tight contact structures, possibly distinct. Okay, and now this is up to now not exactly what I want to get, because I said at the beginning I will construct 3p plus 1 of them, and up to now I just constructed p plus 1 of them. So one thing that I want you to recall is that at the beginning I said this is just basically working on a weighted link, and one interesting property of the weighted link is that it's symmetric. So up to performing an ambient isotopy, I can swap the two portions of the link, and that means that I can actually take this surgery description, isotope things around, and get an equivalent surgery description, but this time the surgery coefficients will be swapped. So I will work with that description now and construct tight contact structure using that diagram. And I will count them, and at the end of this process, I will show you how to distinguish between the ones I constructed here and the ones that I will construct now, and also between themselves in the two families. So just I think do this, which is
Before
Yeah.
much farther, so in creating these first P+1,
Yeah.
you cited something that says the resulting thing would be tight.
yes,
Could you state that again?
yeah. I think
I think the contact invariance is non-zero after.
Well,
yeah.
I just wanted.
I think I hope I'm citing the correct person. If we do, let's say, preserve.
So yeah, so this is the thing that's I thought was kind of quickly schluffed past there.
Yeah.
So you're starting with this right-handed trefoil.
Yeah.
You've got this right-handed trefoil, Legendre right-handed
Yeah.
trefoil
With Thurston Panic number one.
with Thurston-Binnick
Yeah.
number 1. For that guy, if you do
Positive.
positive contact surgery.
Yeah.
Yeah. So in particular the +1 surgery.
Yeah. That will preserve the time.
Then the resulting manifold's tight.
Yeah.
And then
Otherwise,
and then you're doing a whole bunch of negative ones.
yeah. The negative ones are already, let's say, for free.
So because not everybody here is an expert
Yeah,
on
sure.
contact structures in the genre, so I wanted those.
Sorry.
Those are kind of, points that go into why you know this is tight. Right?
Yes. Yeah. As Ken said, like this negative portion is in general will preserve tightness. That's fine. The problem is the +1 surgery I'm doing on the original right-handed trefoil in this algorithm, and due to this theorem here, I know that actually in that case even positive surgery will preserve tightness, so I'm fine with that. And so I start with something tight, and I will end up with something that has a tight contact structure. Yes. So now, as I said, I will swap these surgery coefficients, and I will work with this picture here, which is just the one that has here +1 for P, and here M.
And so, and furthermore, you're saying these are, you're getting P+1 tight contact structures, but have you shown that you haven't shown yet that they're distinct?
No, I will show that. So the point is that a quick preview. Let's say I will construct two families, let's say, of tight contact structures. The one that come from the original description. Then I do this swapping thing on the whited link, and so technically I can already show that these two families, inside of them, they are all distinct. But I think it's convenient to just show at the end that they are all distinct between them as well. So
yeah, I'm
it's
just
just
clarifying that at this point you haven't shown that they're distinct.
No, I just constructed P+1 possibly distinct tight contact structures. So here, what I have to do now is basically the same argument, so I will go more quick just to, let's say, avoid to do the same stuff again. This lemma, I can take this out. So now, as for the, let's say, unknown portion, the continued fraction expansion of this fraction here. First of all, I have to So I swap the coefficients. I first perform the right-handed rows and twists. So now I have, let's say, m p plus 1 over p. Now I do the the right-handed rows and twist, and I get minus 2p plus 1 over p plus 1 here, and well, that's just m. Now I take the continuous fraction expansion of this guy here, which is just minus 2 minus 1 minus p plus 1. So this actually is equivalent to this guy here. Where this is just minus p plus 1, this is minus 2, and this is now I take again a Lagrangian organization of this guy, which is basically the same picture as before. So let me draw it. So this is the Lagrangian organization of the right-handed trefoil. This is the Lagrangian organization of the knots, and yeah, there are just two of them actually. Imagine this is the picture, and so now the contact coefficients, surgery coefficients will be minus p, minus 1, and then minus 1. This is, again, a little bit maybe easier than before. I want to turn, again, this into a sequence of plus and minus 1 Lagrangian surgeries. So this, for this portion here, I just need to stabilize this guy here. P minus 1 times. And for the positive region, as I said before, I just take the minimum m such that m minus 1 over 1 minus n is less than 0. Again, n is just equal to 1. And this becomes r equal to m minus 1 over. So I do plus 1 surgery on this Lagrangian right-handed trefoil, and then I do r surgery on a Lagrangian push-off of that. So I take a 0 push-off of k2, and I perform minus m minus 1 over m minus 2 surgery. To turn this into a sequence of minus 1 surgeries, again, I run the same algorithm. Now what I have to do is take the continuous fraction expansion of this guy here, but this is the same morally as minus m over m minus 1. I just take n plus 1 instead of m. So the continuous fraction expansion of that guy is still a sequence of minus 2s and so on. That's because of the lemma that I stated before. Now these ones are, instead of m minus 1 times, it's m minus 2 times. So what I have to do now is, well, stabilize L0 one time, take L1 m minus 3 Lagrangian push-offs of L0 and do minus 1 surgery on L0, L1, Lm minus 3. So basically, to summarize, I have stabilized this guy p minus 1 times and perform minus 1 surgery on the stabilized and not minus 1 surgery on this guy. +1 surgery on the original right-handed trefoil. Then what I have to do is take a push-up of that, take a stabilization, and then take M-3 push-offs of that guy and perform -1 surgery there. So in total, I have to do stabilization here. Stabilization, and also on this Legendian push-off here. And if I count the possibly distinct stabilizations that I can do, this is actually will produce 2p tight contact structures, possibly distinct. So all in all, together with the p+1 that I constructed before, I get 3 p+1 tight contact structures. And one thing also I want to mention is that now I have M surgery on a M-1 surgery on a TB1 right-handed trefoil, and by another result, I think also by this schematic, but I'm not entirely sure. This actually preserves also Stein fillability. So these 2p contact structures are also Stein fillable. So to get putting things together, I constructed 3p+1 tight contact structures. 2p of them I know for sure they are Stein fillable. Probably also the other p+1, but I don't know it yet. And now I want to show you that I can distinguish them via the contact class in Ungar floor. Basically, I will show how to distinguish these guys up to contact isotopy, and actually tell you that I constructed at least 3p+1 type contact structure that are distinct. So let me decide what I can erase, because now I need some past pictures. Say I can definitely take this out. So now for the for this part, we need two important results. The first is again a theorem by schematic, which says the following: I have M with some contact structure such that site has non-vanishing Ungar floor contact invariant. Contact invariant. And I have omega ji, which is a Stein cobordism from M psi to M prime with psi I prime. So I have two Stein cobordisms from M psi to M prime with two different tight contact structures. If psi prime 1, psi prime 2 are isotopic, then the spin structure induced by this complex structure by J1, J2 are isomorphic. And in particular, same first gen class. So indeed, if these two guys, 1 and J2, are not isomorphic, then the Eger-Floor contact invariance of psi1 prime, psi2 prime are distinct.
Question.
Yes.
Contact invariants are defined up to an overall sign.
Sorry?
The contact invariant is defined up to plus or minus sign.
Yes.
So in what sense they are distinct? They don't become the same for either choice.
Yeah, they don't become the same for each choice.
So you could be working with one, two coefficients.
Oh,
Does it matter?
not really. Yeah. So why is this useful? Well, I mean, our the surgery description that I introduced during the first portion of the talk give rise to Stein coordinates from S3 standard to Ln 2p plus 1. And with some tight complex structure psi, let's say, depending on the stabilization choices I made and how I constructed it, but I have some complex structure. What I can do is I can denote the spin C structures related to this psi here as psi, and what this tells me is that if let's say if I take two different tight contact structure constructed on these three manifolds, call them psi I, psi j, are isotopic, then the first gen class of this spin C structure are the same. Okay, so if I want to distinguish between these tight contact structure that I constructed, what I can do is just show that these guys here are actually different. And so that's exactly what I will do. But to do so, I first need another result that tells me how to actually compute these objects. And this is a theorem due to Dehn. Let's erase this guy here.
How is this least good advantage result related to a similar result on that scale, right? About the linear independence of contact invariance? Did that come after this?
There's a similar result. I don't exactly know which result you're referring to.
It's just that if you have a collection of contact structures, and it's the case where you have more than two, you can say something about the linear independence. So.
Yeah, probably. I didn't saw that result, so okay. Probably
maybe this.
Yeah, really. I don't know.
Yeah. Only one came before the other.
So as for the computation of those guys, this is done. Basically, that's just it. This just says that if I take W, which is a 4 manifold, obtain so on a link which is just union of knot portions Fi containing S3, and I take the contact structure.
Is that a genre link that?
Yeah, sorry, the genre. Sorry. Contact structure induced the omega, and I take mu I, which is the meridians of my link components. Then the Poincare dual of the first Chern class is just equal to the sum over all the components of the rotation number of Li, and this is like a corresponding generator of H1 of So what this tells me basically is that this guy here evaluates as the rotation number of Li to the generator in second homology, which is the disk given by the core of the two handle attached along this link component together with the link disk. And yeah, this is what I will use to compute those guys there, and I will show you that they are actually distinct. So what I will actually compute is this guy here, and you see it's already kind of evident in some sense that different stabilization choices will give me distinct tight contact structure, because these objects here involve the rotation number of the link component, and every time I choose how to stabilize, I decide how to modify my rotation number. One thing that is kind of important is that I could use this result to directly show that, yes, different stabilization choices in between the two families of tight contact structures that I constructed will give me non-isotopic tight contact structures. The problem is that I have two distinct surgery descriptions and two distinct presentations of this object here, this first homology group. And I also want to be able to distinguish up to isotopy between the tight contact structures that I constructed by the two families. And so I need a common presentation. So I need to write down this object in terms of presentation of the first homology that works for both surgery descriptions. So I can't just say directly, oh, they are distinct because I made different stabilization choices, because this tells me that they are non-isotopic just between the families, not in between them. So I need to fix that problem. So this just tells me, yes, one constructs P+1 tight contact structure, all distinct. One constructs 2P tight contact structures, all distinct. But now I have to distinguish between them. And let's do that. It's not hard computation, I think.
So, did you compute the V3?
No, I don't need them.
But you know, if the V3 you can compute from the surgery, but if there are different contact structures.
That's a good point.
Or is it different? So
But doesn't that require also
But wouldn't that only show that they're not contactomorphic?
Yeah.
He's also distinguishing up to
Well, if
isotopic.
they are different, then they are not contact isotopic.
But doesn't that also need?
D3 immanent. So only you need GOF because GOF defines the D3.
Yeah, no, I guess there's potential that you have two contact structures that are related by contactomorphism of the manifold.
But they will have the same D3.
Right. And so if he finds two of the same
Yeah.
D3, he still has to distinguish them somehow.
But
I'm interested.
I'm guessing that since the rotation numbers are different, he will find different D3s from the surgery diagrams. And you have only two components, so the matrix is 2 by 2.
Yeah, I didn't think about that approach, to be fair, but I think
Something to look into.
Yeah.
Suggestion. See if they.
I mean, I don't know. Yeah.
I mean, at the very least, it'd be interesting to see if there's some that are actually contactomorphic.
Contactomorphic, yeah. That's actually.
that would
This
be
is
an
also,
avenue.
Yeah.
also
I mean, because I know that these are actually all distinct, so with this computation, so if that tells me that there are two which the same, they are just contactomorphic but not contact isotopic.
That could be interesting.
Yeah. Thanks. So, I mean, just to let's say make sure that we remember the pictures because I sometimes forget them. So I'm quickly redraw the two families descriptions and yeah, and then do the quick computation, and that will show me that these are all distinct actually. So this is the first one, and I will now compute this object here, depending on the stabilization choice, let's say. So it was this, and this guy goes here. Wait. No, let's go right. Yes. Yes. Sorry. Yes. Remember that in this first thing, I needed to take a Lagrangian push-up of the right-handed trefoil and perform +1 surgery on the original one and minus P +1 on the push-up. I want to go back to the smooth presentation. What I can do is take this Lagrangian push-up and slide it over with over the original right-handed trefoil. This is just this, let's say, way of thinking is just a handle slide, and what this will produce is just an easy cubic calculus thing. It's minus P frame meridian of that guy, and now the surgery coefficients, the smooth ones are just this is -2, -2.
Just so you, I mean, that above that little minus P circle,
yeah,
crossing that needs to change. Just right above it. It's just nitpicking. It's not unlocked, right? Yeah, right now you don't have the trefoil.
This one. Yeah, yes, sorry. Yes. So this is the link, let's say, L, which is Li components inside S3. Now I take the meridians, which are just mu1, mu2, mu2, so on. This is mu m -1. This is mu m. Yeah, my mu is terrible. Okay, and this is mu m +1. And well, the first homology of this guy here has a presentation in terms of these meridians, which is just given by the linking matrix. I will not write it down. but doesn't matter. So the Poincare dual of the first-gen class associated to the species structure of, let's say, contact structure psi, which is one of the p+1 contact structures I constructed, would be given by 0, mu1 plus 0, mu m minus 1 plus 0 mu m plus r mu m plus 1. And this r here is just something inside this set. So one of these p+1 possible values. So as I said, this shows me that depending on my stabilization choice, this r will be different. I have p+1 different choices, and they are all distinct. So this tells me that the ones that I constructed are actually not isotopic between them. But again, I need to give also the other ones and show that they are distinct between the two families. And the other ones, this was the surgery diagram, and here. And this is 2, this is minus p+1, this is minus 2. And now, if you recall, I had to take m minus 2 push-offs of this right-handed trefoil, and I can do the same as before, so slide over as an endo slide over the original right-handed trefoil, and this will produce me, say, m minus 2 meridians of this guy, and the framing, again, is just a computation. This is just minus 1, so I have m minus 2 of them. Then take the meridians here. So this is mu1, mu2. This is mu3, mu4, and so on until mu m plus 1. And I can compute now the Poincare dual here of the first-gen class of the contact structure associated to this surgery diagram, and this is just given by r bar mu1 plus 0 mu2 plus 0 mu3, so on. Sorry, no. Plus s mu4 plus s mu5 plus s mu m plus 1, where r bar is in this family now, p minus 1, p minus 3, and minus p minus 3, p minus 1. So as you can see, I have p different possible values here, and s is one of the two signs, so it's either plus or minus 1. And so you see here I have 2p possible values, and this tells me that, yeah, these 2p ones are actually all distinct between them.
Just for your diagram there.
Yeah.
I think the trefoil should have a meridian that's labeled mu3, right?
Yeah.
And because you labeled.
Oh yeah, sorry.
That should be a mu3
Yeah.
there.
Yeah, this is mu3. Yeah, here. This will always be 0, basically. Yeah. And this is these two objects, and as I said, I now want to let's say show that between them they're actually distinct. So I need to kind of take a common presentation of the first homology class and trace back the isomorphisms in order to show that when I compute how the Poincare dual of the first giant classes is expressed in terms of that presentation of the first homology group, then they are actually distinct. So what I can do is just take the original picture. So this whited link thing, which was like, yeah, the one with the M and T+1, so the starting one. And what I do now is take this guy here, mu, and this guy here, call it nu, and the first homology is represented in terms of mu and nu, with some relation. And now I trace back, basically I have to trace back how to get from here to here, and how to get from here to here, and look at what happens to these guys when I do this isomorphism. And I think I can spare you the exact computation, but turns out that in the end, let's say expressed in terms of mu and nu, I can write it here, so it's a neat, let's say.
So you're just doing curves?
Sorry? Yes. Yeah, basically what I do is like destroy this portion with blowdowns. Here I do a, inverse slam dunk move, and basically cancel out all these redundant generators.
So you defer to go up.
Yeah.
And then you just track.
Yeah, exactly. I trace what happens to the homology classes, and then the right-handed. I have to do the left-handed props and twist to go back to the trefoil, and then for this guy here, I also have to swap, because if you remember this one at the beginning, I swapped. I have to re-swap it again to get that. So it's just an exercise. I think in Kirby calculus, it's nothing too fancy, but it works, does the job, because in the end, I actually get what I want, because these two expressions will now be in terms of mu and nu. One is 0 mu plus 2r mu, where r is that's set there, so p minus 2 minus p. And for the other one, I actually get that it's minus minus m minus m minus 2 s mu plus 2r mu, where s is just a plus minus 1, and this is again that sets there. And yeah, I mean it's kind of easy to see now that these objects can't be the same, because this is 0 and this is not 0. And yeah, that just tells me that actually the Poincare dual of the first child classes of the spin C structures related to the ones that I constructed here and the ones that I constructed here are actually distinct between them. So I produced up to compact isotopic exactly triple P+1 tight compact structures. For the, let's say, K P+1 over P, this calculation is the same. It's just I will produce 4P of them because of some rational coefficient expansion, just different result, but the construction is the same, so it's nothing too deep. And again, this gives me a lower bound for the tight compact structures. And now, one interesting thing is that I can actually compute an upper bound, and this upper bound is given, let's say, by the convex surface theory, and it's strongly for the upper bound, so like a preview thing.
So that's what you're going to talk about next week.
Yes.
Okay. So you've shown the lower, you've constructed these contacts.
Yeah.
And shown their tightness things. A nice topic.
Yes. And now I want to show, well, how many, let's say, possibly how many tight contact structure, possibly this thing, I would be able to construct. If I can show that that number is actually 3p plus 1 or 4, and 4p, then these are actually all of them. And that is exactly what I did. And
it's exactly what you're going to do next week.
Yes.
Okay. I'm just saying you don't have to do it now.
Hey, no, I'm not doing it now.
No, it just sounded like you kept on about this and started describing your.
I just want to say that it's for the upper bound. It's it's really kind of important, and that I will use it. The fact that we are working with this hyperbolic free manifolds, because that's a factor that we use in my proof. And yeah, I think that's it for today. I decided to do two things, which is, I think, natural, and I hope you enjoyed the talk, and thanks again.
Thanks. Any further questions?
If I recall correctly, you assume that that was created at a
Yes. That's the reason for the upper bound, actually.
Okay.
Yes, it's one thing makes calculation in that case way more easier, and also I kind of need in my let's say proof. Probably, I mean, one can drop this assumption, but not for this.
But for today's stuff.
No, that was not relevant. Yeah.
So you just need to have greater than 2.
Yes, because of that zero cancellation. Yeah. I think one can show that you can produce this even, and greater or equal than 3. But that just gives you at least in general. I'd say for greater or equal than 5, I can also get an at most. So that's why I assume that in the theorem.
Well, great. Thank you very much. Well.